So what they give us is a triangle with 3 distinct vertices, yes, but firstly, the camera can't actually capture everything inside that triangle. Some of that area are actually non-existent color perceptions outside of the horseshoe shape of the human observer. Hi there. Welcome to the next video in this series. In this video, I want to just take a little while to discuss some questions and comments that came up on previous videos because I think the discussion is quite fascinating. Generally speaking, I wanted to reflect on the learning process and how we form ideas and how we have theories, how we test them, and how we move forward in our understanding. I find it's better generally on color grading, color theory. It's a pretty intense topic, so I find it's best to maintain a curiosity about these topics and avoid arrogance. Don't assume you know it all. You'll quickly discover there's lots of fine details in between each of those details that you thought you understood so fully. At any particular point in time, our understanding is merely a model that we've constructed in our brains to make sense of a complex topic like color perception or image making. The model is not the truth, the fixed truth, and can never change as such. It's merely a rough working assumption that in some cases might be good enough to just mostly get us through what we need to do. When finding out new information, however, the model must be updated. And we say this is a heuristic kind of method. The Wikipedia entry on heuristic defines it as follows. A heuristic or heuristic technique is any approach to problem solving that employs a pragmatic method that is not fully optimized, perfected, or rationalized, but is nevertheless good enough as an approximation or attribute substitution. Where finding an optimal solution is impossible or impractical, heuristic methods can be used to speed up the process of finding satisfactory solutions. You have probably heard people say that color perception can be a bit of a black hole topic. You can study it for your whole life. It's hard to understand and it's very hard to completely quantify. And one of the main reasons is it all relates back to a person and what a person sees. We're the experiment and the scientist doing the experiment at the same time. So it's a very complex topic and we need these kind of heuristics and critical thinking to help us through this process. And just to show you that this concept is quite iterative, the Wikipedia entry defines critical thinking as follows. I could introduce it this way to say that the current heuristic of what critical thinking is, as written by the people who wrote it and edited in the Wikipedia entry, is as follows. Critical thinking is the analysis of available facts, evidence, observations, and arguments in order to form a judgment by the application of rational, skeptical, and unbiased analyses and evaluation. So this in itself, this definition is, on one level, it's a heuristic that could be updated in the future. We can see that it itself carries references to where these ideas have come from. It gives a whole history. And then right at the bottom, it's got a whole bunch of references. So these are ideas from the past that have been built on to create this summary. And that's very much how ideas in color theory are stacked on top of each other. We can see the scaffolding of heuristics that this heuristic itself rests on by looking at the references. So the way you assemble knowledge is quite similar to this. To give examples from episode 2, when I discussed color spaces and color management, I said the following. I was talking about colors and I said a certain blue that can be defined by a certain wavelength of light. And we got a comment from Paul Hanrahan that very correctly pointed out, in that context, it sounds vague enough to be interpreted as any point on the CIE chromaticity diagram having a certain SPD, which is spectral power distribution, or the power that light source has at each wavelength of light. While that is only the case for coordinates on the spectral locus, as everything inside the spectral locus, so the whole internal body of that CIE diagram, are what's called metamers. And this is just a great reminder on how precise we actually need to be with these terms when we discuss them. The various points along that outer horseshoe do correspond to very narrow band, almost laser-like sources that only emit power at specific wavelengths. And if you show that to a human, that's kind of what they will see, and they'll respond pretty much according to that human observer diagram. The stimulus anywhere on the interior of that diagram, though, would be made up from light that is mixtures that has power at several frequency or metamers. So any light sources, the sun or tungsten light or whatever, has power at a wide range of frequency bands through the visible spectrum. Bear in mind that many different frequency mixtures could result in a human perceiving the same color, and hence the same coordinate on the CIE diagram. So you can have a situation where 2, 3 or 4, 100 or many million spectral combinations all produce the same color to me as the human observer. Only around that horseshoe edge can you take one exact frequency, a very narrow band frequency, and show it to a person, and then that will definitely be that color of what we would call blue or purple or mauve, these kind of concepts which we attach to it once we've perceived these stimuli. So you can see that there's, you scratch a little bit and there's always detail under the surface. In the same episode, I was talking about gamut triangles. I was explaining color spaces when we need gamuts and transfer functions. But I was saying you take the most saturated red, green, and blue, and these three primaries that define what the camera can capture or what a display can show. This sounds like a very neat summary, and it's fine for an introductory episode, but what Carl pointed out very nicely, he said, for displays, yes, we can measure the RGB primaries with a spectrometer and plot them onto the CIE chromaticity diagram, but with cameras, it's not as clear-cut, as the camera observer has different spectral sensitivities, and as such, what's being shown on the diagram when you plot a camera gamut are the maximum code values, not accurate, in quote, colors. When matrixed into CIE capital X, capital Y, capital Z, using the manufacturer's provided 3x3 matrix and plotted onto the CIE small x, small y, capital Y diagram, does not show anything about what colors the camera can and cannot capture. Okay, so there's a lot to unpack here. I mean, what I said sounds harmless. Sure, you've got a camera, maximum red, maximum green, maximum blue, draw a triangle, done. Sounds simple and understandable, but there's more to it. Maybe for an introductory video, that summary is fine, but one must be aware that on each of these topics, there's always more detail to drill down on. So from Car's comment, we can see that there's something called a camera observer that is used to model the way a particular camera is sensitive to light. And every different camera has a different one. This is obviously different from the human observer, which we discussed, which is the CIE diagram, which models the way humans on average perceive light. So that's point number 2. Point number 3 is to note that we have color spaces known as the CIE capital X, capital Y, capital Z, which is basically like a general train station. It's a interchange space that we go from this camera to this display. So often when we're doing gamut transforms, we always route through this XYZ space. And then we also have the CIE small x, small y, capital Y diagram, which is what is plotted mostly for our calibration software and this horseshoe that we're so familiar with. And there is maths to transfer between those from one space to another. What he's also pointing out is that cameras have to take light values that they capture and turn them into digital code values. That we understand. And they have to also make some kind of simplified heuristic, in this case a 3x3 matrix, a triangle, that they feel best maps what their camera captures. Hence, once we have that triangle, then we can best map it into the CIE color spaces. The reason for this is because to integrate into color management systems, they have to give us these coordinates so that they can be implemented in color grading software. Otherwise, they can't access ACES, the Baselight, and all these Resolve with DaVinci Color Management. They need these coordinates so that they can slot this camera into that color management system. But of course, the manufacturers aren't willing to just expose all their trade secrets and tell you exactly what's going on under the hood. But also, the structure is just that give us a matrix, give us a transfer function, and that's how we will quantify and use your camera footage. So what they give us is a triangle with 3 distinct vertices, yes, but firstly, the camera can't actually capture everything inside that triangle. Some of that area are actually non-existent color perceptions outside of the horseshoe shape of the human observer. So those are just specific points that have been chosen such that the triangle also encompasses everything that the camera can capture. But secondly, because the amorphous blob, whatever it is, whatever this camera can actually capture, those data points could, have nonlinear characteristics, and it needs to be best summarized as, or best encompassed by, or best boiled down to one specific gamut triangle before it can be incorporated into color management systems. So there's a lot of detail underneath there, and if you have interest in these kind of things, then just be happy that there's a lot more to study. As a general summary of this, you could say that what we get in terms of that gamut, it's a good enough for now, for general working, creating images and that. It's a map of the territory. But we must remember that that map is not the territory itself, and that the heuristic is not the final truth. There are deeper layers to each of these aspects. We should keep in perspective that on some level of abstraction, all this colorimetry is just a useful heuristic. But also, very important, we mustn't go to the other extreme and jump to the conclusion that hence it's all totally fake and that we're being intentionally lied to by the manufacturers or something like that. So you can put away the tinfoil hats and just remember that do your own research on world affairs definitely does, that way of thinking definitely does have its limitations. Colorimetry is a science and it's been developed for many years. Obviously it's got its pros and cons, and I would say that you definitely have to first spend a significant time learning about the orthodox colorimetry, what they have to say at first, and then you can start prying apart where the flaws in these particular heuristics lie. We also know that whatever information equipment manufacturers put out will have a portion of marketing spin to try and get an edge over their competitors. So we should be skeptical about believing it all at face value. We need to always do tests to see how the equipment actually performs out in the field. I would also add a note to say that it's a problem of our industry in general is that we forget the balance between art and technology. Or should I say technology in the service of making art and telling stories. The story, after all, is the most important part of what we do. Another thing is that we easily believe that something new is necessarily better, which isn't always the case. As a second topic, regarding the node tree structure that we spoke about in episode 3, we had a great comment from Ismail that the scene node is sometimes best placed after the parallel stack where you would be pulling your keys. Now, this is a great topic that I wanted to dive into more. I totally agree with what he had to say, and I just want to highlight some specific examples on when you might move this scene node around. I want to highlight 3 situations. The first situation I want to highlight is a situation where you've been given footage that's been shot at the wrong color temperature. So it's very biased to a certain color, and your goal is to actually get it back into alignment. So this is our basic node tree that we discussed last time. And so we have a scene node here that would be a look for an entire scene, and this would be our shot matching node. And this would be our look and our output transform. I'm just going to hypothetically create the situation that as if the shot has been shot with a very heavy yellow cast on it. So I'm just ignore this node. This is just saying that the footage is actually very yellow. At the beginning of my tree, coming into, after my color management, and once it's coming through the process, pretty much as soon as possible, I want to get it correctly color balanced. And if I go ahead and use this match node, then it means that all my shots, there's no extra variability for shot-to-shot matching. So this whole scene needs to be corrected. So in this case, I would do a scene correction that's before I'd clean up the shot, such that when I start pulling keys, it's a nice clean signal. So you can see that in the case of this biased footage, we want the shot to be nice and well centered on this cross, so that the neutral axis is at the middle of this vector scope, and we have each of the colors evenly spread around it. That's our best opportunity for pulling hue keys and hue, saturation, and luminance isolation. But now in this situation, we've actually been given footage that's very biased to this top left quadrant. We have to now bring it down, neutralize it onto this axis with various primary tools, such that it now is best for keying. So that would be situation number 1. Situation number 2 is, what if you've actually given footage that is shot warm intentionally? This is totally part of the look, and this is what it's supposed to look like. It's discussed by all departments, and this is totally on, it's a period piece, or it's supposed to be sepia or something. This is exactly what they wanted. But you as the colorist, you now have to deal with this problem. Because say they now want to be pulling, you need to pull keys that differentiate the lips from the skin, or the skin from the wood, or colors that are very close to each other. But everything is now covered with a yellow wash. So what do? One thing you could do is do the same thing, do the scene node that takes away that look, with an RGB mixer or with an offset, whatever works, depending on the situation. And then at a later stage in the node tree, you could put that back. You'd have to work out the balances and make sure it was exactly the same. So the net effect was the same, but at this stage. So if I highlight this node, you'll see that it is actually centered on the center, as opposed to there being off up to the top left quadrant. That could be one approach, but then you kind of working forward and backwards, and it might be a bad solution. One thing you could do is make a separate channel that's only for keying. So you're never going to use this in the final image. It's just going to be totally for keying. So I'm going to highlight again just so that we can see what's going on that node. And we can see, well, again, I'm going to have to do my assumption that this is the wash that they actually shot with. So this is the signal that I'm actually getting in the beginning of my node stack. Now, if you bring it here from the beginning, then it's never going to change, which is one benefit. So you can do the balancing to bring it back. You can neutralize it. And then you could also stretch it, because if you're pulling luminance keys on such a small signal, it's also not ideal. So, you could use lift gamma gain to stretch it out, and then, also just balance it slightly better, stretch it out. I mean, it depends how far you want to take this. This already is probably good enough, but you could also increase saturation. You could use, theoretically, very clean ways of introducing saturation, like using the RGB mixer and doubling each channel, which is a very primary way of doing that. And now, this signal's never going to get used. It's never going to get looked at. It's only for pulling keys. So this is your clean signal, balanced signal. And now, from this, you're going to take this as the input to a node where you're going to start pulling keys. So, for example, you would, key the skin tone, and there you would go. You'd see it's a much better starting point for pulling keys now that it's been cleaned up, compared to this, which is all totally washed with one color. So that's one way of doing it. The third example I'd like to discuss is, what happens if we have footage that has been shot clean, but the goal is to put a heavy color wash and change it hugely. For example, a day for night scene. So if we're doing our day for night and we do it here early in the process, then all of our keys here in this parallel stack are in a terrible state, because we're going to make it dark. We're going to put desaturate. We're going to put blue washes on it. The last thing you want to do is put all these distortions like color washes and reducing the brightness range, and then try to pull your keys after that. Best to key off a clean signal. So in that situation, you might do something like this. So for example, we say we have two nodes here that we're going to build. You would build this prior to the fact into your node structure. And let's say that this is the day for night. And what we're going to do here is, well, I'm just going to do it very simply. I'm just going to say we're going to darken down. We're going to take the gain down. We're going to take it a little bit bluer. We're going to drop the midtones. We might even drop we're going to keep black detail. We don't want to clip it out, but we do want it to be very dark and very blue. Then prior to that, maybe we're going to desat, because in dark environments, your eyes don't perceive a wide range of colors. If it's dark enough that you only using the rods in your eyes to sense light, then it becomes very monochrome sense. So we would do this, we'd desaturate, taking colors out, and whatever, the rest is up to you as to how contrasty you wanted to make it. I mean, you could actually do this. You could actually add the contrast first. So it's a contrasty image that has now been reduced down, and that could be your look. All of this happening after our parallel stack. So what these nodes, if we're trying to pull keys here, we've still got a lovely clean signal, which is what we had at this stage. Also bear in mind that these nodes are seeing, they're not seeing this, they're seeing this. Just bear in mind to what the signal looks like at each stage, and that is when you'll decide where to place your scene adjustment. If you do particularly need adjustments per scene that are different to the overall look for the whole show. The broader concept that we're getting to here is that order of operations is very important. We do grade within this 32-bit floating point workspace, which has got a lot of headroom, and details can be recovered, obviously, while it's still live in the grading space. If we render it out to a 10-bit file and then bring it back into our system, obviously the detail, if it's clipped, it's actually been clipped. But while it's live, grading from a raw file, inside of the grading session, you do actually have a lot of headroom. So I'd recommend you do some experiments with order operations just so that you really understand what it's all about. So let's look at some of the basics. So I'm going to save that, and let's just completely reset, and let's just have a bunch of nodes all in order. Let's say, I don't know, one of them could be adding contrast, a whole lot of contrast, like that. One could be desaturation. Another could be color washes, something like that, just to be crazy out here. One could be like an area isolation, so it could be like a window, the outside of which we're going to make dark and blurred. So, I mean, just to be extreme like that. And then in our last node, we're going to key a certain color, and let's say it's skin tone. So I'll label the nodes. So there I've got my contrast first, got my desaturation to black and white, I've got a split tone, I've got this vignette on the outside, and then I've got this node that's trying to key skin tones. And just, you can hold down Control and you can change the order of operations. I mean, the easiest one, the one that really affects what we're talking about here, is this desaturation and the split tone. If we change the order of operations, doesn't matter what split tone you put in here, you can go absolutely crazy with the split tone. Only thing that'll get affected post the node after it is obviously the brightness, because it's 100% desaturated. No chromaticity makes its way through this node in this configuration. However, if we reverse the order, then yeah, all of this makes a big difference. I mean, this is very basic stuff, but it's hard to keep track of this, because also when you're monitoring the signal, you're only looking at the end result. You're not realizing what does the signal look like at this stage of the node tree, even though I'm not monitoring there. So, I mean, personally, I do think that kind of more stages of monitoring is something that's going to be an area in which our grading process will advance to encompass. Obviously, if you want to key the skin tone, you're going to have to do it definitely before the split toning and definitely before this desaturation. So this would have to come right at the beginning here. We can put our contrast in at the end. Obviously, the effect totally changes. And the same thing, what if we actually put at the very beginning of our process, if we went ahead and put this, like this vignette right at the beginning, then whenever we tried to pull keys, they would be affected by this darkening. So it's very intuitive, but especially if you're new to color grading, try this out and just be very aware of order of operations and how parallel and serial structures affect each other, and build your node tree very carefully. Another interesting question we got from Rocking Dude 3001, great name, was regarding the method of adjusting exposure. Just about, do we do it in log with offset? Do we have to do it in linear? What is the best way for adjusting exposure? And I thought the best way to answer this question was to actually just show you how it's been through the ages. And then you can see that the different options and how they've unfolded to us as the systems have changed and developed. Let's start off at the film era, when it's optical projection in cinemas, and all you can do is change the printer lights in the film lab. You shoot your negative. When you do the contact print for making your final print, you can adjust the printer lights, and you've got red, depending if you're going to talk in positive or negative, see the red, green, and blue, cyan, yellow, and magenta, and I think it was a scale of 1 to 6 points of each from normal. So I've mimicked this by saying we've got a standard print LUT here. Prior to the print LUT, we can use printer lights in our primaries here. All we're doing is shifting these printer points up and down, and these are the 3 lights inside of the contact printer where the neg is printed onto a piece of print film. And this is pretty much it. We could make everything darker, everything brighter, and it was the neg curve in front, and it was the print curve behind, and that was it. You couldn't stretch the signal top to bottom. You could either move everything up, move everything down, but you were constrained to the curve. And, other than doing things like bleach bypassing and some, pre-flashing and tricky techniques, push and pull processing, but pretty much it was very much a chemical process and very analog. Offset was the answer. Printer lights, simple as that. The next stage was kind of the Telesin era. Now, what I'm mimicking that by saying it's already formed image. So what we used to get off the Telesin scan was it was already pretty much, you could already look at it as such. It wasn't super flat, it was kind of flat, but a little bit. And then we could adjust the gains, which were kind of like individual channel offsets like this. Red, green, blue, you could set those. But the workhorse, sorry, I should be operating here because we actually work after that. So, we had the primary gains, R, G, and B pickup sensors of the Telesin, but the primary workhorse was obviously lift, gamma, and gain. And we used to grade like this. There was no contrast knob, there was no S-curves, unless you wanted to try and draw them yourself on the custom curves, and the custom curves were very tricky, very hard to use, and very easy to break the signal. Because the interface was small. I mean, just this low resolution SD monitors and this whole interactivity of the GUI space is just worlds apart from what you're seeing now today. So yeah, in this era it was lift, gamma, gain. So exposure changes were lift, gamma, gain, basically. Stretching the signal, pulling up and down like this. You could, as the first stage of setting the Telesin, you would adjust the overall R, G, and B, you'd optimize for each to make sure that they weren't clipping, put them in a good position, balance them out, and then you would jump over into your lift, gamma, gain and keep going. So that in that era, call it the Telesin era, the 90s, all the way up to the like 2013, there. If you were operating a Telesin, then that's how you adjusted exposure. So then jumping ahead, the digital systems come in. The red one is now the camera. All those small Canons, small Sonys, everyone's moving over to digital. The mass use of film is dying. And all we had at that stage is, okay, ignore this. Let's just assume I'm getting, I'm converting from log C3 to log C4 here. Let's just assume I've got the raw file sitting on the timeline. Now, initially, when digital grading came out, it was just this. You were just given the raw file and say, go ahead. Sure, we had S-curve contrast, so cool, we did this, we just built the look. We went like, okay, how much S-curve, how much there, okay, saturated out, stretch, color, and we could do layers at that stage, so we could build up a look, but in terms of color management, it didn't really exist. And very shortly came the LUTs from the manufacturers. So, we're shooting ARRI. Okay, so we've got this, what people call K1S1 or whatever. It's basically the ARRI 709 LUT. And obviously, you can work before it, you can work after it, and then all your tools are still available. At this stage, we did have offset, which is addition and subtraction on the log signal. So that's what we were doing for offset, and that people swore that was as close as you could get to photometric offset. So it's very interesting how perspective changes. Because try it. If you shoot an exposure range from 2 stops under, 2 stops over, so it's actually the camera doing it. You're actually closing down the lens. Compare the two. Then try and balance it back just using this. And you'll see that the rate at which everything moves is you kind of have to pick one range and match it, and then stretch the others to match. Okay, so this was a kind of fairly accurate way to do it, but definitely not the same as the actual exposure changing in the camera. So fast forward again, now we're in the era of color management, where we have ACEs, Baselight has True Light, DaVinci has then come out with their DaVinci Intermediate, and essentially we've got color management. We've got this dedicated, it's not a LUT, it's now some mathematical functions where we can switch from one space to the other. Initially, we didn't have all this mapping, but yeah, we could start doing grading from one space to another. And now this concept of we're not grading in the camera space anymore, we're now transferring to a working space, and then we're adjusting from there. So that was kind of intermediate stage. And because of this stage, you could now say, okay, I'm going to transfer into linear. You'd have to do this kind of stuff. You'd have to say, okay, I'm in DaVinci Wide Gamut now, and I want to now transfer into linear. That's my input. So I'm going to do my adjustments in the middle here. And then after that, I'm going to now do the opposite. So these two make a net 0. It's like a round trip that nets out 0. But in the middle here, I'm in linear space. And so I can do gain, which is now a very close, in terms of physics, is the closest thing to actually changing from log into the linear space, and then just using gain, which is a simple multiplication. So if you want to go up 1 stop, you go to a gain of 2. Go up 2 stops, gain of 4, 8, 16, etc. You'll see it reacts very differently, and it reacts very accurately to matching 2 stops. If you do that camera test where you shoot 2 stops over, 2 stops under, and you try and use this method, you'll find that it is very, very, very close to actually doing it in camera. So this is the best way to do it, and it's what most tools actually do under the hood. As the final stage to this, I would say that where we are now is we also have the color space aware tools. So as long as you set your project and set your timeline color space, or if you want it to operate in a different space, you go into the tool and you tell it which space to operate in, because we now have that function to do that on the node as well. We can tell it which color space or transfer function to work in. Then we can do that, or we can just use these more advanced tools which are color space aware, and that they have, what I really like is this global tool, because it's literally in stops. You can punch in, okay, I want to lift up 3 stops, and that's what it looks like, or minus 3 stops, and it looks like that. And it's, well, near as damn it to exactly the same as just doing gain in linear, and that's probably what it is actually doing under the hood. So that's a kind of a quick tour of offset. Was always there as the way of doing exposure changes. It's just whether you were operating on a log, well, whether you were doing it optically with the amount of light on a printer light in an optical printer, then you were doing it just as an offset in a telecine, in a already pretty much display referred signal. And then we started doing offset on log images. Then we had the ability to transfer into whatever space we wanted. Color management systems came online, like ACES and all these other ones. And then we could literally choose to transfer into whichever space we wanted, such as linear, to do linear gain and all those things. So that's kind of how all those different options came about. And the one that's, the slight different option is if we wanted to go into ACES CC, just as a slightly different, we normally use CCT, but if you wanted to use CC, which is more of a pure log curve, on this side, we'd be going from ACES CC to our display. Then in the middle here, if we did offset, it would also act like a lot more like a gain in linear, but you'll find that there is a stickiness that happens on these very low values. The very, very low values do stay low, but you can just try it out. The behavior of the toe, mid area and shoulders are quite different in using CC, ACES CC, which is why ACES CCT was invented. It was brought about because colorists preferred the behavior of having this toe on the curve. I stand corrected, but it's more like a piecewise curve rather than a true log curve. And then just, if you were using lift gamma gain, it behaved, quite differently to just the Telesin era of just doing lift gamma gain on a signal, but it was closer and more responsive to what we were used to. So yeah, that is a very brief history, and I hope all those these questions, because we can't just run through the stuff once. You have to come back, analyze, and realize where, yeah, your heuristic was good enough, but now needs updating. So yeah, please keep those questions firing, and we can keep looking at this very exciting world of color grading.